So linear differential operator is given by the following form: an dxn dn an minus 1 dxn minus 1 a1 dxt plus a0. So operator is something like operating on the function. So we are going to solve this equation. Equal to 0. So this is called linear operator. Differential operator. For special case when a is a constant, a special case, we have considered the case that an minus 1, a0 are constant. Then we can actually transform this differential equation into the algebraic equation. Then L transforms ordinary differential equation into algebraic equation. Once we substitute trial y as exponential lambda x as a trial function. Because of the properties of exponential function, then the derivative is just multiplying lambda. So that means exponential. You can use either this or braces, or L, both is okay. So L exponential lambda x is actually an lambda n plus a0 times exponential lambda x is equal to 0. And exponential lambda x is never 0, right? For real lambda, exponential lambda x is non-zero. So only possible case is we have something in the parentheses. That means an lambda n plus a0 is equal to 0, right? So by the fundamental theorem of algebra that we have n different separate roots. So lambda can be lambda 1, lambda n. So that means we have the following solutions: lambda 1x, lambda 2x, lambda nx, right? And we can have solution. Therefore, is yx is like a c1 exponential lambda 1x, cn exponential lambda nx. But some cases arise, such as the double or triple root. What happens? So we actually covered in the last class, but I'm going to just repeat it again. What happens if C lambda is something like this: an lambda, say 1 is square. Double root. times exponential c lambda exponential lambda x, right? So we have the following lambda is equal to 0, right? On the other hand, if we differentiate something is wrong with my pen. Probably my pen is out of battery. Let me just check. Just for 5 minutes, let me just use the board. So then c lambda exponential lambda x, say an lambda minus lambda 1 squared. Lambda minus lambda n minus lambda 2. And we know that when, of course, we have lambda x, so lambda is lambda 1. If you substitute lambda is lambda, can you see the screen and the blackboard? Too small? And 0, right? What happens is, if you differentiate by lambda and see what happens, then we have twice of an lambda minus lambda n, lambda minus lambda n minus 1, lambda minus lambda 2 exponential lambda x, blah blah blah, an lambda minus lambda n, okay, lambda n is equal to 0. Square, what am I doing? Lambda minus lambda n minus 2, lambda minus lambda 2 exponential lambda x. We can continue. And finally, an lambda minus lambda n to the square, lambda minus lambda n minus 1, lambda minus lambda 3 exponential lambda x, right? So if we substitute, set lambda equal to lambda n, what happens? Partial lambda, partial n, exponential lambda x, lambda equal lambda n is 0, right? And you can actually, you can put this partial lambda partial into the differential operator. Is equal to exponential lambda, lambda x, lambda n is lambda n exponential lambda nx, right? That means lambda, oh no, x. lambda n x is also solution. Let's hope that this works. Let's see if it works. Somehow I tried yesterday, but the same thing, right? D lambda partial. Oh my goodness. Partial lambda partial c lambda exponential lambda x. So that is the same as that, right? So twice of an lambda minus lambda. Oh, sorry. So I'm going the other way. Square lambda minus lambda 2 lambda minus lambda n minus 1 exponential lambda x blah 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 an lambda minus lambda 1 square lambda minus lambda n minus 2 exponential lambda x. So if we set this partial lambda partial lambda x is equal to 0, is same as x exponential lambda x lambda 1. So that means x exponential lambda 1 x is solution 2, right? So if we have a double root, then if we have a double root, at lambda equal lambda k, then exponential lambda kx and x exponential lambda kx are solutions, right? Also solutions. How about triple root? For triple root, then at exponential lambda kx, x exponential lambda kx, x square exponential lambda kx are solutions. So we can easily find the double multiple root problems. So one good example is exponential twice of dxt plus 1, then exponential x lambda square plus 2 lambda plus 1 exponential lambda x is equal to 0. Lambda is minus 1, right? Double root. So in this case, we know that the solution is given by exponential minus x, x exponential minus x. Very easy. So if you think I'm going too fast, just let me know. Ask me a question. How about something like this? 1. Then L exponential lambda x is given by lambda square plus 1 exponential lambda x is equal to 0. So there is no real root, right? So lambda is given by plus minus I. So imaginary number I square root minus 1. It's imaginary number. So we have a Euler's formula, cosine x plus I sine x, and exponential minus ix is cosine x minus I sine x. These are called Euler's formula. So we have cosine x and sine x are solutions. That is actually, we differentiate it twice. What happens? Minus sine x, right? Same as cosine x, dx squared, d squared, cosine x is minus cosine x. I'll let you have time to digest. And L is given by, oops. Another case is the following form. L is given by an xn dxn dn an minus 1 xn minus 1 dxn minus 1 dn minus 1 a1 x dxd plus a0. This is called equidimensional linear operator. So L I is equal to 0 is called equidimensional ordinary differential equation. This is also the case that we can solve exactly. So we transform the following: yx as y of something zx with z as a log x. Use chain rule dx dyx. You can differentiate by dz y and dx dz, right? So we have learned this about the differentiation of the composite function about 2 weeks ago. It's called chain rule. And dx dz is 1 over x, right? If we differentiate the log by x, we have 1 over x. So this is 1 over x dz dy. Or x dx dyx is same as dz dy. We can continue the differentiation process. So let's say dx dy is same as 1 over x dz dy, right? If we differentiate twice, dx squared d squared y is, we differentiate first 1 over x dz dy plus 1 over x dx dz dy is minus 1 over x squared dz dy plus 1 over x dz squared d squared y dx dz. We apply the chain rule again. Then we have minus 1 over x squared dz d plus 1 over x squared dz squared d squared y. Therefore, x squared dx squared d squared y is dz squared d squared y minus dz dy. We can put this in this way. Dz d minus 1y. So this is actually x dx dy is dz dy. So we can continue this process. So let's say x dx dy is actually dz dy. X squared dx squared d squared y is dz d dz d minus 1y. We can continue this. X cubed dx squared d cubed y is actually dz d dz d minus 1 dz d minus 2y. I like to put this as homework. You can try to check at home. So you just differentiate once more, then you obtain this, right? I think it will take about 5 minutes to show that. And could be also possibly next quiz problem. So we can continue this. X to the n, dx to the n, dn to the y is actually dz d, dz d minus 1, dz d minus 2, blah, 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 dz d minus n plus 1. Using the following transformation, z as a log x. So we can actually transform the linear operator to, instead of dxd, into dzd. So what we have is the following. So let's haven't made a copy. It's time to kiddo. Operate. So the linear operator was given by an n dxn dn a1 x dxt plus a0. But it can be effectively transformed into the following: an dzd dzd minus 1 dzd minus n plus 1 blah 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 plus a1 dzd plus a0. You can effectively transform into the following: pn tzn tn pn minus 1 tzn minus 1 tn minus 1 plus p1 plus p1 tzd plus p0. So differential equation can be transformed into the for complex composite variable z. Therefore, Ly becomes Ly over c over x is bn dzn dn y plus p1 tzd plus p0 y. So we can also, this form suggests the trial solutions, right? Exponential lambda z. So that means we can try exponential lambda z as a trial solution, right? So this is 0, that means exponential lambda z is pn exponential lambda n plus p1 lambda plus p0 exponential lambda z is equal to 0. And you can have pn lambda minus lambda 1 lambda minus lambda n exponential lambda z is equal to 0, right? So that means lambda is lambda 1 lambda n. The solution is the following. Solutions: exponential lambda 1z, exponential lambda 2z, exponential lambda nz, right? Or exponential lambda 1 log x, exponential lambda 2 log x, exponential lambda n log x. This becomes exponential log x to the lambda 1, exponential log x to the lambda 2, exponential log x to the lambda n. And this is actually nothing but x to the lambda 1, right? Exponential log something is the same as the original. So that means x to the lambda 1 exponential x to the lambda n is solutions. If we have a double root, what happens? Instead of x, we just multiply by z, which is log x. If lambda 1 is double root, then exponential lambda 1z and c exponential lambda 1z are solutions, right? And that means x to the lambda 1 log x times x to the lambda 1 are solutions. So let's have an example. Still need to copy. So example, they say x to x squared dx squared d squared y plus 4 dx dy plus 2y is equal to 0. So we transform this into the following, right? dz d minus 1y plus 4 dz dy 2y is equal to 0. dz square d square y plus 3 dz dy plus 2y is equal to 0. So exponential lambda z as a solution, lambda plus 1, lambda plus 2, exponential lambda z is equal to 0, right? So lambda is minus 1, minus 2. So that means exponential minus 1 log x, exponential minus 2 log x are solutions, or x minus 2 are solutions. General solution is the following: c1 x to the minus into the c2 x to the minus 2. They are the general solutions. Another example. So differential equations is supposed to be much easier than the linear algebra, right? Is it? No? How about the difficulty level? Which one is more difficult, the linear algebra part or differential equation part? I think we are more familiar with the derivatives, so differential equation might be a bit easier for you, I hope. Another example. X squared dx squared d squared y plus 3 x dx dy plus y is equal to 0. So that means dz d minus 1y 2 3 dz dy plus y is equal to 0. So dz squared y plus 2 dz dy plus y is equal to 0. So you can try lambda z. That means lambda square plus 2 lambda plus 1 exponential lambda z, lambda plus 1 square exponential lambda z is equal to 0, right? So lambda is minus 1, minus 1. This is a double root. The solution is x to the minus 1 log x to the minus 1, right? So general solution is yx is c1, x to the minus 1 plus c2 x to the minus 1 log x. Another example. Okay, I'll let you copy. I think I'm going a little bit fast, right? So when is the school festival, university festival? Is it next week or 2 weeks from now?
2 weeks from now.
2 weeks from now. And usually the festival week, we have the lowest attendance for the class. And it's a very good time to have a surprise quiz. So I shouldn't announce, but I somehow announced. 2 weeks from now, you might check the attendance. It's just going to be a 10-point problem. Ask your name, but don't write my name. I mean, some students actually wrote my name when I asked. It happens once in a while. So there is high chance of having the lowest attendance from 2 weeks from now, and that is a perfect chance for the surprise quiz. Example. X squared dx squared d squared y plus x dx dy plus y is equal to 0. So if we set z as log x, then we have differential equation can be transformed into the following form: dzd minus 1 y plus dzdy plus y is equal to 0, or y is equal to 0, right? So when trial solution, y is equal to lambda z, then lambda square plus 1 exponential lambda z is equal to 0. Lambda is plus minus I. So that means exponential I log x, exponential minus I log x are solutions. So that means cosine log x, sine log x are solutions. Maybe you can take a 5 minutes break so that I can charge the pen again. It's probably good time to announce for the second quiz. May 28th. Second quiz. Oh. 이게 왜 이러지? 한 번씩 시간이 되면 꺼지 알아서. 켜진 거야? 네, 저건 켜졌는데. 켜졌는데. 이렇게. 뒤에는 켜져 있는데. 지금. 이런 잠깐만 해제했던 거 그지? 화면 아까 뭐 살았는데 여기 있는 오케이, 땡큐. To somehow continue the so second quiz we are going to have on May 28th. So after the whatever we covered after the quiz, first quiz, and whatever up to the previous quiz will be the topic. So most likely differential equations, I think. And it's going to be another 2-hour quiz, so maybe you can prepare 2 pages of cheating sheet. So we are going to cover the next topic, like inhomogeneous differential equations. The right-hand side SF is called the source term. And this is called inhomogeneous differential equation. Inhomogeneous ordinary differential equation. So step is the following. The first step number 1. Homogeneous ordinary differential equation px dx squared d square y qx dx dy plus rxy is equal to 0. So they are the solution of the homogeneous differential equation. Let's say yh1x, yh2x solutions. Equation number 1. And we assume the particular solution is the functional combination of this form. Assume that particular solution of the, say, let's say 1, 2, 2 is the solution of equation number 1, the original equation. Form ypx is u1x yh1x u2x yh2x such that we have some following constraint: dxt u1 yh1 plus dxt u2 yh2 is equal to 0. This is a constraint. It's called constraint. You will see why I put this condition more clearly if we proceed some more steps. Then dx dyp is the following: u1x dxt yh1x u2x dxt yh2x, right? And we have the following term: dxt u1 yh1 plus dxt u2 yh2. But this term is 0 by constraint, right? From this. And if you differentiate it twice, dx squared d square yp is, we have the following term: u1x dx squared d square yh1x u2x dx squared d square yh2x plus dxt u1 dxt yh1 plus dxt u2 dxt yh2. So if we substitute this into, this is equation 3, this is equation 4. So if we substitute equation 3 and equation 4 into the original equations, let me see. Okay, I will let you copy. This is a very important step. And I don't want to go too fast. So substituting equations 3 and 4 into equation 1, we get something like this. Px dx squared d squared yp, qx dx dyp, rx yp is equal to, if we substitute the following term, u1x px dx squared d squared yh1, qx dx dyh2, 1 rx yh1, u2x px d squared yh2, qx dx dyh2, rx yh2 plus px times dx du1 dx dyh1 dx du2 dx dyh2 is equal to s over x. What happens to this? So yh1 is a solution of the homogeneous differential equation, right? So what will happen? This will be 0, right? And this will be 0, 2, right? Because both yh1 yh1 is a solution of the homogeneous differential equation, and yh2 is also homogeneous differential equation, right? Solution of. So these two must be 0. Then we have the following term. So that means we have, therefore, dx du1 dx dyh1 dx du2 dx dyh2 is equal to s over x divided by px. And from the previous constraint, we also have the following constraint. Dx du1 yh1 dx du2 yh2 is equal to 0, right? So I'm going to copy this. Copy. And next, paste. So we have the following solution, something like this. We have yh1, yh2, dx dyh1, dx dyh2, dx du1, dx du2 is equal to 0 px s over x, right? So we can call this as A. And you can find the inverse function, right? Determinant A, yh1 dx dyh2 minus yh2 dx dyh1, which is sometimes called Wronskian, is non-zero for. This is called Wronskian. So A inverse is given by one over Wronskian dx dyh2 yh1 minus yh2 minus dx dyh1, right? So you can actually solve this equation as the following form. Okay, I'm going to let you copy. I think I'm still going too fast. Therefore, dx du1 dx du2 is Wronskian times dx dyh2 minus yh2 dx dyh1 yh1 and 0 Wronskian px over x. Oh no. Let me double check. So dx du1 is actually minus Wronskian px sx times yh2x and dx dyu2 is Wronskian px s over x yh1x. Or u1x is given by the following: minus some integral px prime s over x yh2 x prime dx prime u2x yh1 x prime dx prime. So particular solution can be given by the following form. Still need time to copy. So particular solution is now given by the following: minus yh1x times this x wx prime px prime x of x prime yh2x prime px prime plus yh2x s of x prime yh1x prime tx prime. And general solution is the following: c1 yh1x plus c2 yh2x plus ypx. This is the solution. Let me see some particular example. And I'm going to cover only the second order inhomogeneous differential equations, which is probably about the right level of difficulty for sophomore. So any questions? If you think I'm going too fast, it's about the time to ask me a question. Okay. One example. So yh1 is, say, cosine x, yh2 is sine x. Maybe I changed my mind. Sine x, cosine x. Wronskian is yh1, yh2, dx dyh1, dx dyh2, right? So this is sine x, cosine x, minus cosine x, minus sine x is equal to minus 1, right? So Wronskian is minus 1. Px is 1. Sx is 1 over cosine x. So we have Wronskian minus 1, s of x 1 over cosine x, px is equal to 1. So yh1 was sine x, yh2 was cosine x, right? So u1x is actually x minus 1, 1 cosine x and minus cosine x dx prime x, right? u2x is minus 1, 1 cosine x prime sine x prime dx prime x cosine x prime dx prime cosine x, right? ln cosine x t. So this is ln cosine x. So solution is the following. Particular solution is given by x sine x plus cosine x ln cosine x. So I will give you homework. Solve 3 similar problems. So you design second order differential, inhomogeneous differential equation, 3 cases, and solve that for your own benefit. I think you can check out the internet or any other engineering math book or any differential equation books you can find. So this is one very simple example. And probably stop today. I think we covered enough material for this week. Okay, so 2 weeks from now, we are going to have 28th, so 3 weeks, right? From now, we are going to have a quiz. Actually, my original plan was after 2 weeks, but that happened to be your festival week, so may not be good for some of you because you like participating in the official functions for that. All right, so see you next week. So thank you. You don't have to follow. Yep.
마지막으로 질문 한 번.
네네.
이전 강의에서도 이제 오늘도 그 X 저기
로가리즘을 했어요.
아니 그게 아니라 갑자기
부정적분.
요게 왜 이게 다 붙는 건지, X 프라임 왜 붙는 건지.
그냥 X 함수 표시하려고. 이게 최종분 X가 나올 거예요.
네.
그러니까 뭐 이거는 안 붙여도 돼, 상관없어.
오늘 그럼 하신 거 중에서도 프라임이 붙어 있는 건 다.
그냥 헤드가 안 해도 되고.
네, 알겠습니다.
네. 아니요, 저번 포함 안 해요. 저번 본 다음부터 다음까지.
이걸로 올라왔던 강의인데
네.
여기서 일로 어떻게 넘어가는지 모르겠어요.
어디서요?
여기서 이렇게 더 넘어가는 과정을 모르겠어요.
아, 여기서 원래는 아마 이거일 거야, 그지? 네, 이거는 적분이 잘 안 되잖아.
네.
1을 더하고 1을 빼면 어떻게 돼?
그냥 의미 없어.
근데 1 더하기 탄젠트 제곱은 뭐야?
시퀀스
네. 그죠?
네.
이거는 시퀀트 x의
미분 형태.
미분 형태 되는.
네.
그럼 마이너스 x 이렇게 되죠.
네. 근데 여기 마이너스 1이 아니라 x인 거예요.
아, 마이너스 1이 빠졌네. 그지? 마이너스 1. 이거는 이거지. 잠깐, 이게 좀 이상하네. qx가 여기 마이너스 1이 있어야 된다. 이거 많이 빠졌네.
아, 네. 감사합니다.
네.